Right everyone, today we are going to solve a problem called detect cycle in an undirected graph. I've already made a video on detect the cycle kind of in a directed graph, which is done by using Kahn's algorithm using BFS. But what if our graph is not directed, it's undirected, right? So let's understand the question. So given an undirected graph with v vertices labeled from 0 to v minus 1 and e edges, and we have to check whether it contains a cycle or not, and we have given an adjacency matrix, or you can say an adjacency list, and that have all the nodes, and we have to find out, hey, do we have a cycle in this graph or not? So we can do this either with BFS or DFS, and I'm gonna talking both of the approach in this particular video, and I've coded both of them since it's a long code and I don't want to waste your time just coding and thinking. So I've coded both of these approaches, and I'll explain you what exactly is happening here, right? So let me tell you what will happen. Let's start with the BFS, right? Let's say we have this graph. Let's draw this graph. So we have 0. Let's change the color. Now 0, right? We have 1, then 2, then 3, then 4, right? And no, it should not be a directed edge. It's just an undirected graph, right? And what do we do in BFS? We take a Q, right? So let's take a Q, right? And let's say since we don't know like which node to start from, right? Let's first start from 0th node, right? So what is BFS? Initialize the node, put it into our BFS queue, right? Our queue, whatever you can name it, right? But the extra thing that we're gonna do here is we're gonna also store here the parent that this particular node came from. So something like this. So let's say if our first node is 0, so it came from nowhere. So we're gonna write 0 comma minus 1. While q is not empty, we're gonna pop it. We're gonna pop a 0. We say, hey, we have visited 0, right? And which are our neighbors of 0, right? So we have only one neighbor of 0, that is 1, right? And we're gonna enter, and we say, hey, enter its neighbor, but where did it came from? 1 comma 0, right? Then again we say, hey, pop my 1, and add it to our BFS traversal, right? And it came from 0. Let's see how many adjacent node 1 has. So we can clearly say it's 0, 2 and 4, right? So we have 0, 2 and 4. Let's try adding 0. So we can't add 0 since we already found 0 in our traversal. So then we say, hey, is this a cycle? Since we found a node that we have already visited, that's why we are passing this parent node. So we say, hey, it's not a cycle. How can it be a cycle if I already came from there? It is my parent, so of course it will be my adjacent node, right? So this is not a cycle. Then we are going to enter 2, right? Let's enter 2 here, and 2 came from 1. Sorry. And then we have 4, right? And 4 came from 1. So again we're gonna see, hey, our queue is not empty. Let's pop 2 comma 1. We are going to put 2. Since we have not already found 2, right? And then we say, hey, what all are 2 neighbors? So as we can see here, we have 1 and 3. So we found 1. Are we gonna put 1 here again? No. Why not? Because it's already present in our BFS queue, right? And BFS list, right? And how we know this is not a cycle? Because 2 came from 1. 2's parent is 1, right? That's how we know. So we just keep on traversing, and we add 3 to our list since 3 is not present. So here we're gonna say 3 comma 2 because 3 came from 2, right? Then this pops up, right? Then we have 4, right? So we have 4 in our list. So 4 comma 1, we're going to say, hey, let's put it on our BFS list since we have not seen 4 yet. So what are 4's neighbors? So if we see 4 neighbor are 1 and 3, right? 1 and 3, exactly. So we try adding 1, but we already have 1, but we are not gonna say, right, we are not gonna say, hey, we already found 1, but 1 is 4's parent, right? This 1 is 4's parent and we have stored that, we don't care. Then we second neighbor is 3, so we again going to add 3, right? So we're going to add 3 comma 4, right? Then we say, hey, we are at 3 comma 2, pop this, right? We're going to pop this 3 and we say, hey, which are 3's neighbor? So we say 2 and 4. So 2 is okay because 3 came from 2, right? It's okay because 3 came from 2, right? But when we found 4 again and we see, hey, 4 is already present in our BFS, but 4 is not the parent of 3. That means while traversing it into a BFS pattern, we found a node 4 that was not the parent of 3, right? But it was not the parent of 3, but still we found it. That means it's a cycle, right? Let me I'll show you the code, then you will have a greater clarity on this. So let's just let's just forget about this is cycle function and this focus on this helper function that will help us to go traverse the from a starting node, let's say 0, it's going to traverse and tell us, hey, if there's a cycle or not. So as I said, we are going to make a queue, right? And we'll add initial start node with the parent as -1, so since it didn't came from anywhere. So while queue is not empty, we're gonna say, hey, take out that member, right? And I have already made a pair class, so I can save these node and parent easily. So I'm gonna pull out, I'm gonna take the element in the queue and I say, hey, give me the value of the current node, give me its parent, right? And then I'll mark it as visited, right? After it's marked visited, I'll add its corresponding node, right? And I'll traverse all its corresponding nodes and say, hey, only add it into the queue if it's not visited, right? If it's not visited, add it in the queue. Else, if it's visited, what do we have? If it's visited, there can be 2 conditions. Either it is a parent, since it came from there, of course the parent will exist in the adjacency list, right? So if it's a parent, we don't care, it's not a cycle, right? I mean, this 1 2 can't be a cycle. Let's say if only 2 nodes were there, then also if we go on to 2, we again find 1. It's not a cycle, right? Parent and child can't be a cycle. But if the node that we found is visited and is not a parent, then we know for sure it's a cycle, right? It's 100% sure it's a cycle, right? And then we return false. Now let's come to this main function is cycle. So as we are making a visited array, right? And for every vertex from 0, since it's a 0 indexing, right? And we have v vertices, we're gonna say, hey, if the current vertices is not visited and the helper function, what our helper function returns is, it returns false if it's a cycle and true if no. So whenever this returns false, that means we have a cycle, so it will go inside a loop, and this particular function will return true if it's a cycle and false if it not. Then you might be thinking, why am I calling this for each and every node? Why? Because if you see, there's an example. In normal case we don't have to, right, this kind of graph, but here if you see, this is the disconnected graph. The 0 is independent and 1, 2, 3 are independent. Let's say, there was a cycle in here. Let's say my node 0, right, and then 1, then 2, then 3, right. Let's say it's connected like this, right, and let's say we start with 0. We say, hey, 0 is there's no adjacent node to 0, so then there's no cycle. If we just stopped at that and didn't call any other nodes, then it will return false while there exists a cycle in a part of the graph. So make sure to call for each and every vertices. And then again one question might arise, hey, since we are calling for every vertices, it will run for every vertices, then it can be a bad time complexity in case of this case, right, since it will run for every vertices. But no, it will not be the case. Why? Because if it's a connected graph, even if I ran from 0, this will traverse literally everything, right. It will go deep, right. If in BFS it will go here, then it will go here. So it will find a cycle and it will mark all the node visited, right. That's why I am checking here. If it's not visited, then only call this helper function, right. So that was our BFS code, to check a cycle. And I've also written helper 2. This will be your depth first search, right. And the depth first search will be nothing. It's almost the same as BFS, just that we won't be using a queue. We'll use recursion, right. And an additional variable will require parent, and whichever node we are at, we'll say, hey, visit, mark the current node as visited as true, right, and get the current node's adjacent members. And for every neighbor, if it's not visited, just recurse on that choice and see if it's returning false. If it's returning false, that means there is a cycle, right. Else, if visited, if we have not visited, right, and if it's not a neighbor, then also return false, right. If this particular recursion returns false, that means this whole value becomes true. That means if any of its neighboring or any of its child node, you can say, return false, we will return false. We don't care, right. Or if it's not visited, right, if it's visited and it's not a parent, since in every iteration in every recursion we are passing the parent, right, and if it's not a parent, then also it's false. We found a node which is not a parent while traversing in a DFS pattern. And if for every of its neighbor we succeed, and we didn't go inside these loops, then just return true, right. And I've already compiled this and I've already run this. This will run perfectly fine. If you want, I'll add a code to GitHub link to this particular code, and we can just submit it, right. You can do it in either way. The important thing is to understand the BFS and DFS and how they actually work, right. This might not come as a direct question, but this is very important in graph to be understanding this whole concept of how you will find a cycle using either of them. You have to be comfortable with BFS and DFS. Alright, I think this is the first time I've tried this drawing everything and explaining. I hope I am sure it's not much clear, but it will improve over time. Thank you.